Hello, everyone. Let's talk a little bit about some topics, some select topics on momentum and energy conservation. That'll help you on some of the homework that you do and some of the examinations that you do. I'm going to try to unify both a non-calculus approach and a calculus approach. Those of my students that are in the non-calculus version of this material don't need to know the calculus. And those in the calculus version of the material, it's good if you know all this stuff. It could be to your advantage. Also, many of the people that are in the non-calculus version of the class have a calculus background. So it's good to look at this stuff as well. But should be some pretty decent content to look at here. Certainly not all of it from a calculus background. So I'm giving two perspectives here. For mechanics treatment of some topics related to momentum conservation, energy, and energy conservation. And that's what I have written right here. I'd like to kind of look at the problem. One of the problems that we had, it was, I think from the CATS book for the calc treatment, but I've done this problem with the non-calc classes as well, guys. Basically, it's a classic pulley type problem. Let's look at it. Let's analyze what's going on with it, and let's maybe look at it from the perspective not only of forces and tension and things of that nature, but also from the perspective of energy conservation and how energy gets dissipated due to friction. When there's friction to be overcome, energy is always conserved. Momentum is always conserved. Energy is always conserved. Momentum is always conserved. So where does that energy go if we're talking about friction? Well, it goes into thermal energy, but the energy does go somewhere, and it is accounted for. And as long as we, as I've mentioned in lecture, as long as we know how to do the accounting, we should be okay for doing a lot of this stuff. Well, as we look at this, guys, let me try to kind of go into to this a little bit. I mean, like I said, this problem there was a problem very similar to this in the book, and like I said, it's just a classic problem as is. You can find them just in numerous textbooks, calculus treatment and non-calculus treatment for that matter. As we look at this, guys, let's say these ropes are very, very long, very light. This phenomenon here is taking place high up somewhere. Gravity is the gravity associated with the gravitational pull of the Earth at around the Earth's surface. So the gravitational field is G, which is about 9.8 meters per second, or 9.81 meters per second. This is a classic scenario. They are holding the weights until somebody hits the stopwatch or says go, and then they release the weights, and we'll see what happens. There are a number of things that can be said here, guys. So let me get the title here off here. So as we said here, this is some select topics on momentum and energy conservation. And let's kind of draw some conclusions. Let's talk a little bit and draw some conclusions. We're allowing for friction to be present in this scenario. So if there's friction present, there's also the fact that, well, look, the pulleys are very, very light, and they don't have any friction. There's no friction associated with the pulleys, and they're very, very light, both pulleys. The ropes are very, very light, and M3 is much more massive than M1. And M2 is intermediate in mass between M1 and M3. This will not contribute to any of the motion. The tug of war takes place right here, as we've said many times. M1 is pulling down this way. M1 is M1 associated with gravity. In other words, M1G, M1 in red here, M1G is pulling down this way, and M3G is pulling down this way. It doesn't take much to figure out that this one's going to win the tug of war. The acceleration this guy's going to accelerate upward. This one's going to accelerate sideways, and this is going to accelerate downward. And let's ask some questions here. I'd like to know what the tension is in the ropes. Now remember, the way this is pulling, it's kind of an action-reaction sort of thing. as this pulls down, you know, as it pulls down, the tension, it's also pulling this. But, you know, Newton's third law, that's why we got the tensions going as they are. There's sort of that idea. You pull, you're also getting pulled back on. So as it's going right here is there's a tendency to want to go this way. This thing somehow pulls, this weight is being pulled, but at the same time, it's kind of pulling back. So everything's going on right here, as I've said in the past in lecture. We're doing it with friction present. We've done this problem. Depends what class we're talking about and at what point we're doing something like this. At various times when I've done this sort of problem, you guys, we're looking at a few things to kind of keep in mind when we're doing this stuff. We'll call small f the frictional force, and you know, small f is the frictional force, and that's mu sub k times n. The n is the normal force, and this thing's horizontal, so it's mu sub k m2g. And so we know that. I guess what I had done, let's just stick with what I had done. It just makes the math easier, you guys. I'm not having to calculate it live while I'm trying to do the actual problem and get filmed on it. Mu sub k we'll say is 0.2. And as I said, the masses are as follows. M1, M2, M3. M1 is 3 kilograms. M2 is 5 kilograms. M3 is 8 kilograms. So we're looking at something like that, you guys. Okay, and we're trying to find, well, I mean, initially we're trying to find this, but there's a lot of things we can try to find, I guess you could say. There's 3 unknowns there that we will initially try to find. Again, we need 3 equations and 3 unknowns. We have 3 unknowns. I need 3 equations and 3 unknowns for this to happen. Now, we've done this in the past, you guys, so I don't know, whatever. I'm looking to build to something a little bit different, but repetition like this is not the worst thing that we can deal with. Got this. We got that. Okay, so there's basically 3 scenarios they talk about here, guys, that are of interest to give us the 3 equations. And like I said, there's different ways questions can get asked related to problems such as these. So let's just take a look at it and see what we can do. You kind of ignore everything else in the universe other than what's circled here in green. Same thing here. You ignore everything else in the universe except for what is circled here in green. Same thing here for 3. Scenarios 1, 2, and 3 will give us 1, 2, 3 equations. This thing pulls up, and then it pulls that way too. Anytime it pulls, it's getting pulled. So it pulls here, but then it gets pulled. It pulls here, then it gets pulled. So you're kind of looking like that. Let's see what we got here. And we said there was going to be, there's a frictional force to overcome, you guys. Because we said there was going to be friction present. We kind of stated that in pretty blatant terms here, guys. The result of this tug of war is, the result of this tug of war between T1 and M1G, T1 wins it because everybody's going this way. This wins the whole thing. This beats everybody. So everybody's going clockwise. This is T1 minus M1G. The difference between the two is M1A. And so let's proceed with this argument. You've seen this happen, guys. M1A, there are ways we can do this. Here's an equation 1 for you. Here's an equation 2 for you. These two guys do a tug of war. This one wins it. Not only that, it also defeats friction. So friction and T1 are together. T2 goes that way, and T2 beats both of them. By how much? It's going to be M3A right here, and it's T2 minus T1 minus F. Yeah, well, the F is the mu sub k times the normal force. That's mu sub k times M2G. Mu sub k times M2G. Third one. There's a lot going on here. Bottom line is this one wins it. M3G minus T2, the difference between that is M3A. All right, so we got guys. We got this situation. And from here, you're just solving 3 equations and 3 unknowns. We've been down this path. I've done this in person at some level or another many times over numerous semesters, I guess you could say. So I mean, I know the classes have seen it either in the notes or in person or in both. But it's still important to, I mean, like I said, when we can talk about it a little bit more, we can talk about it. At the end of the day, there's a lot you can say, but let's just go for it. I mean, what I've done in the past is I say, well, this equals that, this equals all that, this equals all that, and this equals all that. Add all the different thises with all, so what you do is this number 1 scenario equals all that, number 1 scenario. This number 2 scenario equals all that number 2 scenario. And this number 3 scenario equals all that number 3 scenario. Add the left-hand side, add the right-hand side. Left-hand side, M1A plus M2A plus M3A. All these A's, you can take the A out of there, guys, and you have this. T1 and a negative T1 is 0. T2 and a negative T2 is 0. You got, so the T1 and negative T1 cancel. T2 and negative T2 cancel. That's it. You got M3G minus M1G minus mu sub k M2G. True. So what you have here is, you write it down. You've got, and there's a lot of G's here, obviously. You got M3G minus M1G minus mu sub k M2G. There's G's all over the place. Pull the G out of there. We're looking at that situation, guys. Let me just see that it looks okay. On the camera, we should be okay. Yeah, it looks all right. Not great, but okay. So the G's out to the end over there. If you're going to divide by all this, just straighten it out here. It's what's over here. This is a G right here, guys. That's a little more clear, I hope. What do you got? You got M3, M1, There it is. There's your acceleration. Again, you plug in the numbers and everything else is going to be fine. So the end of all that, guys, you get this. You plug in the numbers, you get answers, obviously. When you plug in all the values, you can solve for T1 and for T2. There's a myriad of ways, not a myriad of ways to do it, but there's a number of ways you can go about doing it. Again, they already told you what M1, M2, and M3 are. When you do this math right here, you're going to find the acceleration. Just plug in M3, M1, and plug in M1, M2, M3, mu sub 2, or mu sub k rather. I'm sorry here. You plug in mu sub k, M2, M1, M3. You know what G is, 9.8 meters per second, and you're going to get A. When you do all that, you can plug in, well, you already got a value of A, you already know what G is, you know what M1 is, solve for T1. After you solve for T1, I mean, there's a lot you could do. You come back here if you want. You don't have to mess with this, actually. You go here, you can add a T2 on each side and subtract M3A and just do the math, you guys. All the algebra that I've shown you, and this is on Canvas as well, when you solve these three equations and three unknowns simultaneously, you're going to get the values that you're supposed to get. Again, and not to make this, I don't want to belittle this whole process, guys, but just for the sake of it, get T1 by itself to solve for T1. You add M1G on each side, and you get M1G plus M1A. M1G plus, let me just see here real quick. Yeah, correct. M1G plus M1A, so you can kind of write it like that for shorthand. And then T2, go down here, you can add a T2 on each side and subtract M3A on each side. T2 equals M3G minus M3A. G minus A right here if you want to take it in a little different manner of looking at it. So this will get you the T2, that'll get you the T1. You already got the A. Let's just put the numbers in there. And actually, that's it. I mean, on that. Now, there's some questions you can ask and maybe should ask. Again, we're assuming these ropes are very, very long, very, very light. The pulleys are frictionless. There is a surface that has friction, and we've accounted for it. But let's say they're really long, they're high up in the air, so we're going to allow this thing to fall down. I might want to know how long it takes for this thing from time t equals 0. Time t equals 0, there's no acceleration whatsoever. I mean, or at least none that's manifested. What you do is, bam, right when you start it, that's when they start going. Well, okay, that's the acceleration that we're seeing, right? That's obviously the acceleration within the system, how this thing is moving. Well, we got all this, so we just get rid of it now, and we'll talk about it from there. So we've got, don't want to erase all of these, I guess. Take this out of there. Okay, so look, at the end of the day, guys, I mean, we grind out all the numbers, we do what we're asked to do here. We were able to figure out some things and get ourselves in a spot where we can answer more questions if they want to ask us more questions. 2.45 meters per second per second. T1 is this, and we said there is a difference when there's no friction, how the tensions all play out. So there it is. Okay, great. Now, what does somebody want to ask some questions? Well, there's a lot of room here, a lot of rope, a lot of everything. How long does it take for this thing to fall 40 meters? That's a big number. I mean, whatever. But let's say it was going to take what do you mean it falls 40 meters? It falls 40 meters, man, means this thing started here and it goes 40 meters. Let's say there's a really big experiment here. We're talking about hundreds of meters long, and the rope is very, very light. All the rope is very, very light. The pulleys are frictionless. The pulleys are massless, frictionless. The ropes are very strong, also massless. And but there is going to be friction. But there is going to be friction here. It's a long, long table, and hundreds of yards long, whatever. Let's say whatever it is, whatever the device is for the, for the experiment that we're doing here. What do you want to say about this? What's going on? Well, I mean, we know enough that it starts at 0. We know a whole lot, actually. We know, how fast is it going to be going after, how far did it go and how fast is it going? It's a good question. This thing fell 40 meters. What does that mean? If this thing fell 40 meters, this thing moved over to the right 40 meters, this thing moved up 40 meters. This guy moved up 40 meters, this guy moved over to the right 40 meters, and that one went down 40 meters. They all moved 40 meters. So they're all moving here. Okay, they're connected, they're moving. What's going on here? We know that, distance is VIT plus 1/2 AT squared if you want to go that way. How long does it take to go that long? How's it going to happen? Well, there's a lot to be asked here, guys. Let's go for it. I mean, initially I was holding the weights, so they weren't moving at all initially. So you got D is equal to 1/2 AT squared. Let's see how long is it going to take for it to fall that way. I mean, if you can do something like that. Let me multiply by 2 on each side and divide by A. Let's square root both sides. T equals 2D over A, square root of that. Well, excuse me, guys, got to get my calculator here to see what we're going to say about it. I mean, the T, a lot you can say. I mean, T is going to be this. It's going to be the square root of all that. I mean, what is it? Well, we just said it's a rather elaborate experiment if we could pull it off, I guess. But I mean, the concepts are what we're really aiming to get under control here when we're doing this. And again, there's going to be round-offs and things like that to some level, but let's take a look at it. You got something like this. The time it'll take for it to fall 40 meters is given right there. Five point 5.714, something like that. Absolutely. How fast is it going at that time? So, and this is kind of be of interest. And the reason I'm doing it like this, guys, kind of show you the unity of the logic, if for lack of a better way for me to put it right now, guys, the consistency in the logic and in the operations that they're doing in physics. We can go about it in terms of forces. We can go about it in terms of conservation of energy. That's a big thing. So let's see where that's going to go. Well, we also know, okay, we did all this. We also know the speed at that time. I mean, I don't know. How many ways could you play this? You know, that's the thing. Tempting to look at it a number of ways, isn't it? The final speed after that many seconds equals VI plus AT. Well, we said VI. I was holding it before this whole thing kicked off, and we got 2.45 meters per second times 5.714 seconds. Times 2.45. Yeah, according to this, 14 minutes is going pretty fast. I mean, 14 meters per second at that instant. Now, could you have done it another way? Yeah, I mean, you could have gone here. You could have said, hey, D is VF squared. And these square things are pretty interesting. It's looking something like this. We knew initially the VI squared was 0, as we said. So D equals, you know, there's a lot of ways to go here, guys. Let me kind of. That's 0. You got VF squared here over 2A. Why don't you multiply by 2A on each side? Multiply by 2A on each side and square root each side. You got 2AD square rooted. There's the 2. There's the 2.45. And there's 40. Okay, I ran out of room, guys, but this is all they're all multiplied together. You know, and you get 5.9, you get 59, you get 256, and you get the square root of that, you know, something like that. So I'm hoping it's the same answer. Let's see here. Let me see for some reason here, guys. For some reason, this is not looking good, but let me see, 2AD. I got that. I'm trying to see where the other one would be. Got the acceleration looking like that. Right, because I think when we did something, when we did it another time, we got some other answer. So this had to be smaller. Oh, forgive me here, guys. This is 4.9 rather. I'm sorry. Yeah, okay, this would be fine. 2 times 2.45 is 4.9. 4.9, 49 times 4 is 196. The square root of 196, man, why even write it down again? It's the same thing. It's going to be that, yeah. It works out pretty good. We got the time, and we got the, you know, so look, we looked at a couple different ways to get there. Now look, what if you were using energy considerations to get this thing under control? Well, look, man, if we have this physics well under control and well understood, and we're making the right decisions as far as solving the problems is concerned, I better be getting, for the fall down time, somewhere very, very close, I mean, within reasonable error limits. I should get the time it takes to fall down 40 meters. I should get that time to be 5.714 seconds. I should get VF to be 14 meters per second. How would you do that? Well, okay, we remember what we got here. We're claiming we got it under control. Let's just, for the heck of it, let's just leave it up there. Where's this stuff coming here? You're going to see some similarities, And we better see the same exact answer if we're doing this right. If we're confident we're doing this right, we better be doing it right. See what we can say here, guys. As far as energy considerations are concerned, let's not even worry about this. Let's not worry too much about it. We got these answers. They're great. We can kind of ignore that we got them if you want to just look at energy considerations. I mean, what is, just in terms of energy considerations, what's the acceleration? What's the kinetic energy finally? What is the final speed of the system 40 meters after 40 meters of falling? How long did it take to fall 40 meters? Well, we said this is the speed after falling 40 meters. We said that's the speed. We also said that's the time it takes to do it. Kind of ignore this right now and just say, can we do this another way? Well, I got an idea. I mean, we said energy is conserved. We said momentum is conserved and energy is conserved. So we're very adamant about that. So and we know how to do this stuff. So we say, okay, if energy is conserved and momentum is conserved, let me just move this a little bit if I can. What we got? We already got the numbers here, guys. You can obviously go back with the film. You got, when I'm doing this live, I'm not going to be able to do that at that moment, but that's okay. We know where it's at. We've got our answers, so we feel pretty good. You know, we talked about if you pick something up, you're talking about and moved it upwards. That's how much potential energy you got. If you got a spring, force constant k, the spring constant k, and you move it through a distance x, it's 1/2 kx squared. And we talked about kinetic energy. You know, so this right here is the association of kinetic energy, and these right here are both associated with some kind of potential energy. So potential energy associations here, potential energy association here, kinetic energy association there. So here's kinetic energy, and these two pertain to potential energy. Well, I'll tell you what, if we're talking about a 40-meter fall, we're talking about this thing sliding for 40 meters and fighting friction for 40 meters. What does that mean? Well, that means it's going to do all that work just to overcome friction, and it's got to be accounted for. The big thing here is some odd things are going to happen here. Well, we already know, just looking at the system and given what the magnitude of the masses under consideration are, we know this thing is falling. On the right-hand side, it's falling down. On the left-hand side, it's falling up. On the table, it's going to the right. We know all that. And, well, what happens when this thing falls up? When it falls up, when it climbs, this system is gaining potential energy that it did not have earlier. When this thing falls, this thing's losing potential energy that it did once have. This thing was elevated higher, and it lost potential energy. You know, this guy gained potential energy. M1, this mass, there's been a gain in potential energy over here. What is it? M1G climbing to a height h, or to a height d. I know I've been saying h right here, but in this case, we've also been using d. So it's going to climb M1GD. This one's going to fall M1GD. Yeah, but there's going to be kinetic energy all the way around. They're all moving. So, yeah, this guy lost a lot of potential energy. Some of that potential energy went into giving this guy more potential energy. This one lost a lot of potential energy. So where'd it go? Well, it ended up speeding up. It ended up giving this guy, it ended up speeding everybody up. It lost potential energy. It sped up everybody. Lost potential energy, gave this guy potential energy in addition to speeding everybody up. And this guy got sped up and went that way. And they fought friction. what's going on here? Well, I think we just said it. I think what we have is we've got, I guess we could say a couple things here. We could say that M1 plus M2 plus M3, all three masses are moving with a speed v sub f at the bottom after the 40 meter journey. They're moving like that. So that's all kinetic energy from the potential energy. In addition to that, kind of see exactly how I want to write this, guys. There's a number of ways to write it. So there's all that kinetic energy that it's got. True. Let me write it. I'm going to write that. Absolutely, I'm going to write that again. But let me do so carefully, I guess you could say. Let's say initially. Let's see initially what's going on. It's the same things that can get written again, ladies and gentlemen. That's not going to be an issue. We've got a situation where this much potential energy, M3GD or M3GH, that pertains to this, and they pertain to, like I said, these pertain to potential energy, you guys. All of that loss of potential energy, yeah, but not quite. There was also that gain of potential energy. That gain of potential energy. So it didn't all, all of this loss of potential energy went to a number of places. I mean, there's so many ways to write this, guys. Forgive me here. Let's kind of take, I guess we could say this is big brother to the whole system. This M3GD falling down, that loss of potential energy went to give potential energy to the M1 because it climbed. It also went to do all this work against friction. And at the end of all that, so many ways to write this, guys. I don't know the best way to write it. I do know that there's a number of ways to write it, and mathematically they're all identical. To me, this maybe, obviously I wrote it like this, so I'm thinking it's maybe the most straightforward way to go when you're doing this thing. Basically, I'm saying that the one that's kind of given up, the real big mass that's giving up all that potential energy is going to accomplish something. What is it? Well, the large mass falling this distance through a gravitational field G is it lost all of this potential energy and it gave some potential energy to the climbing M1. It gave some of that potential energy to the climbing M1 and also gave some of that potential energy to defeat friction. And then whatever was left over went over here for this thing to move. Well, notice friction does really hamper things because if you subtract these two quantities on each side, this guy by itself makes sense why it's not that much. So you can say a lot of stuff here, guys, if you want to do this. The way we're looking at it is basically 1/2 And we can use the kinematics to find other stuff. But right now, let's find some stuff here. Subtract all these, and what is F, you guys? F is mu sub k m2g, the force of friction. Mu sub k m2g. Well, leave this guy alone. Take this. Leave this guy alone. Subtract these two. Subtract whatever the magnitude is of these on each side. And what we got is, the D's there, the G's there. We've got M3. You're not really sure how you want to go here. That's M3 minus M1 minus mu sub k M2, all of that times GD. The GD is there all over the place. That's what it is. At the end of the day, do the mathematics, guys. Multiply by 2 on each side, divide by that whole quantity, and then get the square root. You're looking at VF is equal to the square root of M3, M1, mu sub k, M2. And this is, 2GD, so I had the 2 in here somewhere. That looks kind of familiar, big time. So to have it here, that's that divided by 1. I just have it here over to the side. But we understand. I'm hoping we're going to get the right answer here, too. When you look at it, 358, 0.2 is 1. So let's see what we got here, guys. We've got 8 minus 3 minus 0.2 times 5, which is 1. Divided by the sum M1 plus M2 plus M3. So it's basically 4 divided by 6. 4 divided by 16 is 4. 4 divided by 16 is 4. Forgive me. 4 divided by 16 is 1/4. 1/4 times 2 GD is GD over 2. So we got 9.8 times 40 divided by 2. Okay, 9.8 times 40 divided by 2, square root that. Yeah, no surprise here, guys. It's working fine. There's a whole bunch of things you could say here. So you've got that. I know it looks awfully familiar. That's what we got earlier. And yeah, I mean, everything's consistent. You can do it with energy considerations and be just fine. Okay. See what else I can say here, guys. Well, we got that. What kind of acceleration is that? Well, how long did it take? I mean, there's a whole bunch of questions to ask. We're assuming there's constant acceleration here. We already kind of figured that one out. But, you know, so what do you want to say on that? You could kind of go back to the kinematic equations. At some point, you're kind of compelled to go back to the kinematic equations to look at some of this. But you could say, well, you know, where'd that acceleration come from? We got d is equal to vf squared minus vi squared over 2a. Multiply by a on each side and divide by d. Vf squared minus vi squared. Well, vi is 0. You got 2d here. You square this, you got 196. 2 times d is 2 times 40, which is 80. 80 goes into here. Essentially, if that were 200, 200 divided by 80 is 2.5. This is 1/20th less than 2.5. That's 0.05 less than 2.5. So 1/20th less than 2.5 is 2.45. And that's that. When you grind it out, you're going to get the 2.45. So that's looking pretty good too. How long did it take for that to happen? You could play that a bunch of ways. If it's a constant acceleration, and it is, you could do everything. You can do everything that I just did earlier and get the answer. Bottom line, guys, they want you to get the answer. They want you to know what you're doing and get the answer. Can you also say that the average of the initial velocity and the final velocity, please note this only works when there's constant acceleration going on. It only works when there's constant acceleration going on. When you look at something like this, the initial and the final added together divided by 2 is the average speed. D is equal to, D equals the average velocity times time. Isn't time the same as d divided by the average speed? Well, the d is 40, guys. The average speed, this thing was going 14 meters per second to end it. It started at 0. For constant acceleration, you can average the high and the low, whichever one that may happen, whichever one's which, doesn't matter. Average the high and the low. 0 and 14. 0 and 14 are 14. Divided by 2 is 7. So you're basically saying here, you guys, 'Don't want to erase any of it, actually, but okay, so we got 0 and 14. VI was 0, VF was 14. VI plus VF over 2 times T is going to be equal to D. Let's make the long story short. This is 0, this is 14. 0 and 14 is 14, divided by 2 is 7. 7T equals 40. Divide by 7 on each side. 40 divided by 7 is 5 and I think that's some of the answers we were getting last time. Well, let me see here. Right. 5.714. We said that last time. There's a number of ways to go here. 5.714 seconds. And again, that's what we said last time. So there's a number of ways to go here on that stuff, you guys. We're looking at it. Let's look at something else. Okay, I'll be back in just 1 second, guys. I'm going to clear the board and set something up for us. All right, guys, welcome back. We're going to say that there's like a rod, a rigid metallic rod that is attached somewhere, and as we said, the metallic rod is rigid, so it's not going to give way at all. There's going to be a bullet fired at it, or fired at the wooden block that there's going to be a bullet fired at the wooden block that is held by the metallic rod. The wooden block is mass capital M. The bullet is mass small m. It's negligible in size compared to the block. The bullet is much less massive than the block. It hits. It hits the block at a speed v, and leaves at 2/7 of the speed at which it entered the block. So what happened here? What's going on? There's a number of looks that can be given regarding this. So let's see what we can say here, guys. This thing, it gets hit in such a way that this block barely gets all the way to the top. Again, it's rigid. The block is here. The metallic rod is rigid. It'll come right up to here. It'll come just barely up to here, and then bam, it'll fall down again. But it can just barely get up to here. Well, what's going on here? Quite a bit going on. I mean, for our purposes, we're saying that momentum is conserved. So initially, this was not moving at all. The bullet has mass m, so momentum initial equals momentum final. Let's see what's going on here. Well, initially, the velocity of the block, we'll say, is v sub b for the block, and v. Now be careful here. What's what, right? This is the velocity of the bullet, v, and then from there we can kind of determine a few things based on what they're telling us. Initially, there is the velocity of the block initial is nothing. The bullet is moving mv, and this is capital. It's going to equal v sub b. That's the initial, and then this is v. This is going to be v of the block final. We'll just call it vb. vbi is the initial of the block, and that was 0. It's not moving. Bullets moving like that. You got this, and then the bullet also leaves. M 2/7 v for the bullet. So what happens here is, we're looking at a situation where, say a whole lot of things on this whole process, I guess you could say. You could say that, okay, well, if this is going to be the way it is, you got this right here, let me subtract m 2/7 v on each side. This is 7/7 mv. This is 2/7 mv. Subtracted on each side, you've got capital M VB equals 5/7. Let me see here. Yeah, right. 5/7 MV. divide by capital M, the V of the block, after it's been hit, is going to be 5 mv over 7 capital M. So initially not moving, then it's moving, and there's a whole lot going on here. That's small m, this is capital M. Forgive me for really accentuating it, I guess you could say. So what do you know? What's going on here? Well, this guy, the capital M, has enough kinetic energy that all of its kinetic energy is dissipated in making the climb. How high a climb is it making here? Assuming no friction. Otherwise, there's no friction as far as associated with the, with where the metallic rod is attached and stuff. It climbs L and another L. It climbs 2L. Climbs 2L to the top, just barely makes it there. In other words, it has all its kinetic energy went into mg. That's all its kinetic energy went right into that. True. I mean, what would happen vis-a-vis that? Let's see what we can say here. Okay, right, and so all the kinetic energy. We're not really talking about the bullet right now. The bullet helped us get the answer as far as what VB is, but that's it. So what we have here is 1/2 capital M VB squared. 1/2 capital M VB is 5 mv over 7m squared equals capital M G 2L. So, I mean, there was another problem. For some reason, I'm associating it with something I don't want to associate it with, but right. Right, it's problem number 72, chapter 11. Very similar. Problem number 72, chapter 11. Let's just make sure we're on the right. Well, you guys don't have to. Doesn't really go there with you guys on that, but let's see what we got here. I think it's a good problem anyway. Just kind of look at it for the future. A pendulum consists of a wooden bob of mass m suspended by a massless rod of length L. A bullet of mass small m, much less than capital M, is fired horizontally with a speed v. At the bob, it emerges from the bob with that much. If the pendulum bob just barely reaches the highest points, it is able to swing. Find an expression for after the collision. So the way this is, guys, I mean, for some reason I thought they wanted us to kind of get rid of the small m or ignore it, but I don't think you really ignore it. You need it for the actual process of finding what's going on here, guys. I think what's really big here is, even though it's another at least for the 209 people, this is another chapter. For the 120 people, this could easily be fair game, something like this. The big thing to look at here, arguably, it's fair game as is anyway, because there's energy conservation, which we've already discussed, and there's momentum conservation, which is being discussed. So, what's present, what's not, that's its own story. But as you do this, guys, if you want to do this, let's have a look where you actually would actually find what's going on here. Let me just take a quick look at this. Okay, guys, thanks for the wait. Yeah, absolutely. I mean, theoretically, I mean, this is a different type problem than you're going to encounter exactly word for word, but it is. If we've discussed momentum and if we've discussed conservation of energy, we've discussed momentum and discussed conservation of energy, this certainly fits the profile of such a problem, regardless of where it's formally located. Conservation of energy and conservation of momentum, theoretically, you could get asked a question like this. So I'll give you an explanation to a question like this. I just wanted to kind of verify that, guys. We did have to indeed remember that momentum is conserved and energy is conserved. So energy is conserved, momentum is conserved. We used conservation of momentum to get to here, and then we solved for V sub B. V sub B is V of the block. V sub B is V of the block. Confuse that with bullet, I guess you could say. Block. So V sub B is V of the block. We said initially the block ain't moving, the bullet's moving real fast, and then the bullet loses. So, I mean, we're saying initially the block is not moving, the bullet's moving real fast. Initially the bullet's moving very fast, the block's not moving, then the block does move, and the bullet also moves. Well, from there, from conservation of momentum that we've talked about, we should be able to find something out here. And so, I mean, we look at it and say, okay, well, I've got this. This is the initial momentum of the system. Block not moving, block does not have momentum. Bullet moving very fast has a lot of momentum. All of that momentum is conserved. The block no momentum, bullet a lot of momentum. Some of that is the momentum, vector sum. They all go in the same direction as we have it depicted here. All that momentum initially present is the same momentum finally present. The block is moving now, and so is the bullet, but much slower. From there, let's find what V sub B is, and we did. We found this after the collision. That's a valid question. It's a valid question to ask in and of itself. Well, in terms of what we've been told, what's the V of the block? Okay, and like I said, the B can be pretty confusing in its own right, but we're talking about block on that. And well, the kinetic energy, it's all kinetic energy initially. We're not worried about the bullet right now, just the kinetic energy of the block. I mean, obviously, there's in the whole system, there's a lot going on here. It gets this kinetic energy, but I'm just worried about the kinetic energy of the block because that's accounted for here, and it's only the kinetic energy of the block that's going to be accounted for here. It doesn't matter what the bullet's kinetic energy is leaving this. It's the block itself that gets put up here. The bullet doesn't go up there with the block, so therefore we're not going to worry about it. Bullet just goes straight out. The block itself and the block, only the block is climbing up here, so that's conservation of energy problem as well. All of the kinetic energy, V sub B squared, is this quantity squared. All of that kinetic energy becomes potential energy. Capital M, capital Mg, a force capital Mg through a distance of the quantity L plus L. mg times 2L. All of the kinetic energy became potential energy. That's fair game. That's fair game. Even if the formal problem is found in another chapter based on things that we discussed and studied, that's something that one way or the other you could see something like that, because it pertains to conservation of momentum and conservation of energy. Well, there is a lot going on, and this is quite the problem, I guess. You got 1/2 capital M, 5 mv over this. If you square all this, man, it's going to be nuts, but let's go. You're getting 25 small m squared v squared over 49 capital M squared equals capital M G 2L. Now, we've said a lot, guys. I got to erase a little bit here. Some I'm just going to have to leave up there, some I don't. You can always go back. So, well, I mean, there's a load there. I mean, I guess the question would be at the end of all this, what's the speed of the bullet? What's the speed of the bullet in terms of everything that's given to you there? Well, okay. I mean, there's just a lot here. I mean, you could look at it and say, why don't you get v squared all by itself? That's the speed of the bullet initially. The bullet was going v initially, and that's this right here. And that's v squared, and the rest is like, yeah, quite the mess. Multiply by 2 on each side, and you got a 4 right here. Multiply by 2 on each side, you got a 4L right here. 4L capital MG. 4L capital M G, multiply by 2. This right here, the M and the M squared cancel, is just an M down here. So multiply by M on each side. So these M's cancel, you just got one M down here. Multiply by M on each side. Then multiply by 49 over 25 small m squared. No, let me not do that. Let me multiply it by 45 over 25 small m squared. Yeah, that'll work. Let's just make sure it works. M, G, 2L, M and M squared, they cancel. You multiply by capital M on each side. You got M squared here. You got M squared G, 4L, M squared G, 4L. We got that. 49 over 25 M squared. Looks good to me. I mean, there's a lot here. There's a lot here, but actually we kind of luck out in a sense. Like I said, I made this one up based on a previous one, but let's see where the heck this thing goes. It looks like it's pretty good. Square root both sides. The only real square root peculiarity, I guess you could say, is LG or GL. Sure looks like it. I mean, GL, that, GL, square root of 4 is 2. Square root of capital M squared is capital M. Square root of 49 is 7. Square root of 25 is 5. M squared there. Yeah, let's see what we got here. Square root of 4 is 2. Square root of that is that. Square root of 49, we can get the square root of both sides, 7. So 2 times 7 is 14. Capital M. Square root of 25 is 5. Small m. Kilograms and kilograms cancel. Kilograms and whatever the mass units are. Kilograms and kilograms cancel. This is going to be meters squared per second squared. It's going to be meters per second. The units are all there. I mean, it doesn't mean the argument is completely right. Let me just kind of see where the one in chapter 11 is a little different dynamic, but not much. There it is. It's got the same. Yeah, it's the same argument. They got a little different argument when they do it, but so that's a little. It's in terms of the chapter. If you're in my calc-based physics class, this right here is found in another chapter beyond what we've been doing, but the concepts of conservation of momentum and conservation of energy are spot on. I mean, they're not, so in that regard, it doesn't matter what chapter it's found in. If we've been talking about conservation of momentum, and we've been talking about conservation of energy, this is a valid problem that you should be able to do. Okay, I don't know that I'd ask you this problem, but I mean, it's a valid problem in that regard. There's, see where else here, guys. There's another one that's more straight out from chapter 10. Now this is more ballistic. Again, this could be. Notice there's no calculus here, guys. The big things that won the day on this one was there was momentum, conservation of momentum. Initially, the block ain't moving initially, right? Not moving at all, but the bullet's really moving. And then the bullet passes through. It's going at 2/7 the speed of what it was initially going at. So it's getting out of there at 2/7 v. Right, so you got yeah, and at that point, yeah, something's been transferred over to the large block, you guys, and it is going. It's going some v sub b, as we said, and we're going to have to deal with that. Well, yeah, that v sub b is all of the kinetic energy. We've already talked about kinetic energy too. All of the kinetic energy of the block initially, right after the impact, all of that is going to make this thing make a climb of 2L. And so you're caught right here. You're solving, you're taking this, and you're taking this. And this one was from conservation of that. This right here is from conservation of energy. So we've got conservation of energy, and we got conservation of momentum. We have conservation of momentum, we have conservation of energy. Here's your conservation of momentum, here's your conservation of energy. At the end of all of that, you solve, and it looks very similar to the problem in chapter 11. I've changed it a bit, but I think it was like problem 72 from chapter 11. So, and that's fully solved for you. So it's a different chapter, but again, technically, guys, we do know what conservation of momentum is, and we do know what conservation of energy is, and how to apply it. We've done that. Not that you're going to get thrown that, but it's something that could be in the cards, right? So just kind of watch out for that. Certainly down the road, this is absolutely fair game at that point. If you look at a problem from chapter 10, it's kind of got its similarity to it, I guess you could say. You know, they talk about problem number 70 in chapter 10, and both these are from the CATS book, okay, from the calc treatment. But as I said, guys, you did not, for those of you in the non-calc treatment, this is like a classic problem. There's no calculus in it, so it's a classic problem for anybody in a calc-based course or for anybody in a non-calc-based course. It's all very useful for us to be able to do something like that. And it's, you know, there's no no calculus involved in doing something like that. So they talk about, you know, chapter 10, problem number 70 for the people studying with the CATS book for the calc-based physics. That's a good problem too. They talk about it. It's in there as well. Let me go on a little bit to something else though, guys. I mean, let me look at as we're kind of looking at something like this. Let's look at you know, a momentum problem involving a rocket. And like I said, in both books that are getting used, at least for the classes that I'm teaching, they give the exact same equation with different language, I guess you could say. A lot of ways you can say the same thing, right? So let's try to just give it a quick look and see what we can say pertaining to it. All right, guys, there's as we said, you can talk about the rocket problem, and let's talk about it. Let me try to unify it, I guess, with both approaches, non-calc and calc treatment. Basically, guys, for the calc or non-calc treatment of the whole topic, how you want to look at this. The derivation itself is not very difficult, and through a common sense look at what's going on with the circumstances, you can kind of evaluate what's going on with signs and stuff like that. But we need to be kind of careful when we're doing some of this stuff. For a rocket, the change in the rocket's velocity is equal to the vector. These are all vectors now, guys, and so we'll talk about that. Treating vectors, velocity like vectors, and they are. the change in the rocket's velocity is equal to the velocity of the exhaust relative to leaving the rocket times the natural logarithm of the mass of the rocket final after all the fuel has been burnt, or all the fuel that's being burnt that we're talking about vis-a-vis this. And so divided by this. Now I'll try to get into this with people, guys. I'll try to talk to you about it. The force thrust vector again is VE vis-a-vis in relation to the rocket, and D, gets a little touchy with this whole thing, guys. Well, I mean, this gets kind of a little on the touchy side, guys. The thrust is going to move us in the direction in which the rocket is moving. If this is regarded as a negative number and this is going opposite to the direction of the rocket, negative times negative is a positive answer, and that'll be positive regarding in which way the rocket is going. The velocity of the exhaust vis-a-vis the rocket, the velocity of the exhaust in relation to the rocket is a negative number because it's going opposite the direction in which the change in velocity is taking place. So we'll say the rocket's going that way. We'll call that a positive. I guess we can call it positive. What you call positive, what you call negative is an arbitrary thing. But once you make the decision to do it, you have to stay consistent. Basically, I mean, let me put it. I think we're used to seeing vis-a-vis the number line. We're looking at to the right is positive, to the left is negative. If that's positive and VER is negative that way, a negative number times a negative number. Why is this a negative number? This is the mass of the rocket after a particular amount of fuel has been burnt. This is the mass of the rocket before that fuel has been burnt. This is a small number. This is a big number. Small number divided by big number is a positive number, but it's a ratio that is equal to something less than 1. The natural logarithm of something less than 1 is a negative number. Negative times negative will give you a positive answer. And I've done that in lecture too. We've talked about that. And this, like I said, will give us the way this proceeds as well, guys. Now, so, I mean, the Serway book, non-calc version of some of this discussion, gives a pretty good look at some of this stuff. And you can kind of paraphrase it a little bit when you're talking about it. How you want to talk about it, that's a good point. So I want to kind of use the same language for everything I'm doing. This is in terms of calculus. This doesn't matter, calculus or not. You've already done the problem to get it to here. So for anybody doing it, the equations are identical. They derive and they come down to here. In the non-calc treatment, this would be delta MR over delta T. Delta MR over delta T, or delta M. So there's a lot of ways this stuff can be written, you guys. Depending what book you're looking at, follow your book, I guess you could say. The Serway book handles it really well, at least at some level. They're saying, okay, why don't you talk about the rocket having a particular mass M, and it's got, and we'll say there's a mass M. Its true mass is capital M plus a little bit of mass that it's not expelled in exhaust. So it's here, and the rocket's going V when that's happening. when it does expel the mass, delta M, the rocket no longer is capital M plus delta M. It's just capital M, but it's going a little bit faster. It was going V, but now it's going delta V because it expelled some of the mass that was there. Initially, this is the total mass of the rocket at a particular instant. Capital M plus delta M, that's the initial mass of the rocket regarding a particular instant as the initial evaluation of what's going on. Capital M plus delta M is the initial mass at some point. It's going, the rocket with this mass on it, delta M, capital M plus delta M, with all that mass, the rocket's going V. When it expels delta M, there's only this much mass left, you guys. It expelled delta M, so it's not, so it used to be going V, now it's going faster. Well, what happened to the delta M? The delta M went the other direction, actually. It got expelled the different direction. So it's delta M plus, well, here we go. The rocket's going V, but the exhaust is going negative VE. So this is kind of how it goes. Well, if you kick this around, capital M times V plus delta M times V equals capital M times V plus capital M times delta V. We'll get into that in a second. And delta M times V minus delta M VE. The VE is actually a positive number, but you put a negative on it because it's going out the back of the rocket and the rocket's going forward. So you look at something like this. Well, if you subtract capital MV from capital MV, you got this. If you subtract delta MV, you know, if you subtract capital MV, subtract capital MV on each side, subtract capital MV on each side, subtract delta MV on each side, and you got 0 equals M delta V, M delta V minus, see what we got here, minus delta MVE, minus delta M VE. There's a lot you could say, and the way they go about it is a little different. They kind of make, yeah, for you guys in the non-calc version, they do some stuff. I found a little bit confusing, but so what we have here is the whole lot here. I mean, the delta M is a negative delta M. So there, I don't know, it becomes kind of a linguistic thing here, guys, when we're looking at it. You can look at this and you can essentially, you know, you can leave it as is for now. The big thing in terms of the magnitude of what's going on here, this is going on over a period of time. So you could almost, you know, there's a whole lot you can say here. You can get the delta M over there. M delta V, delta M over there is delta M VE. This all happened during a period of time, delta T, you guys, when you're doing this. So what you have is something like that. Well, this is mass times acceleration. Mass times acceleration in terms of magnitude is the rate at which mass is being expelled times the velocity of the fuel leaving the rocket. Makes sense. If you're expelling, if the exhaust is being expelled at a tremendously high speed, the exhaust is being expelled at a tremendously high speed and there's a lot of mass being expelled per unit time as well, these two big numbers should equate to a lot of thrust. And that's essentially what this is in a much more, I could say, elaborate manner, or more of a calc-based manner. In the non-calc-based manner, right here is about right. You know, the way the Serway book kind of wants to discuss it is its own interesting point. But now, I mean, that's a very, so this is very interesting how that goes. And this pertains to the thrust. And the way the Serway book does it, I'll write it the way Serway writes it as well. It's the same language, you guys. It's just different words being used within that same language. The same reality is being discussed. As we look at this, you got something like this. You know, there's a whole lot going on here. I mean, you could multiply by delta t on each side, and you got m delta v equal VE delta M. Well, the delta M is really the change in the rocket's mass, so you might as well call it capital delta M. They were kind of going like that, but they kind of did some stuff with the signs that could, hard to say how, I'm sure they're right, but I don't know how helpful it is in the discussion sometimes. Here's M delta V. Here's VE delta M. Well, the delta M is really a delta capital M. Divide by big M, delta V equals VE delta big M over big M. Yes and no, I guess you could say. I mean, when you're looking at it, to find the delta, to really find what the delta V is going to be, this is at best an approximation. Why are they writing something different than what I just kind of wrote right here regarding this? You're actually, a whole lot going on here. The way to actually find specifically what it would be to make this a dV and make this a dm over m and then do the integral is what's going on there, guys. So kind of keep an eye on that. Let me just write this out. For those not taking the calculus-based course, but you have calculus background, you'll see this, you'll understand it. It should be pretty straightforward. You're not going to get tested on it if it's now we're doing some calculus-based stuff, so you wouldn't get tested on the actual derivation of something like that. However, when it's like this, you know, for the thrust, you know, to find the actual, this right here would be the thrust. This is fair game. I mean, I'll get, you know, we'll talk. Let me just kind of unify both approaches here. I'll write down what's there. This is for calc-based. And even the way that gets written is its own. I mean, there's ways this stuff can be derived, make some sense out of it. So let's see what we can say here. It's an approximation when you're talking about the deltas. It's much more accurate. And in fact, if we believe the functions that are given to us, should give us very close to an exact answer, if not an exact answer, if we're doing a calculus-based approach to the whole topic. Well, we're saying that the rocket blasts off from outer space. Initially, the rocket's in outer space. It's not moving relative to the Earth. And so we'll say its initial momentum is 0. Momentum initial equals momentum final. That sounds familiar. We're talking about conservation of momentum again. The initial momentum is 0 for the whole system. It's kind of like when we talked about there was that experiment that was going to be done where people set up an explosive device far away from people, and they hanged it onto a particular post and said, well, let's see what happens. Let's all go far away, and let's have this on film, what happens in the middle of the desert here when this is detonated. Well, initially, the 500, you know, the 1,000 kilogram bomb, the 1,000 kilogram explosive device had no velocity associated with it. So there was no momentum. When it was exploded, all the pieces of the explosive device that were flying everywhere, their vector sum remains 0. Yeah, but an individual piece has a tremendous amount of momentum. There's practically countless pieces like that. There's very many pieces like that have a tremendous amount of momentum by themselves in terms of magnitude. Their vector sum adds up to 0. So that's kind of what this is. There's a controlled explosion going on with the rockets. The center of mass is essentially unchanged, and the momentum, the momentum of the center of mass is unchanged. It's 0. The momentum of the center of mass is 0. I mean, it's kind of like when I was standing with there's an experiment again, a person standing with a small child, and the small child pushes the person on the ice. They're both on the ice. The small child pushes the person, and small child pushes the person, and the person goes flying, and the child goes flying even more. And their initial momentum was 0. The vector sum of their momentums, even though they're both moving quite a bit right now, the vector sums cancel out, and there's 0 momentum final, just like there was 0 momentum initial. So that's kind of what's going on here. If you take, let me just lose the vector notation for a second. Just do the derivative with respect to P. It's the derivative of this. Derivative of mv with respect, derivative of the momentum with respect to t, you get this. That's dm dt v plus m dv dt equals 0. Well, sure. I mean, if that's the case, go m dv dt, leave it alone. Add a negative. Well, time out. Who's what? The differential amount of matter, and this is for the calc-based, and then I'll kind of throw it out the window and just give you the solution to what it is. And that's what you have to use if you're in the non-calc-based class. For the calc-based class, it's the same thing. It's a matter of being able to use what's already derived. It's nice to look at, though. A differential amount of matter is expelled from the rocket, and it's moving at this speed. That matter that's been expelled from the rocket is VE. This guy right here is V of the rocket. The mass of the rocket, how's it moving? The mass of the rocket, this pertains to the mass of the rocket, how it's moving means what's the velocity of the rocket, what's the change in velocity of the rocket with respect to time. That pertains to the velocity of the rocket. DMT is differential amount, matter is being expelled from the other side of the rocket, propelling the rocket forward. This is going backwards. This is propelling it forward. Well, the differential amount of matter being, well, it's a differential, but it's actually a substantial amount of matter as time goes on. All the matter the rate at which matter is being expelled pertains to the exhaust velocity. The mass moving pertains to the rocket velocity. So you've got to write it like that. If you do that, subtract, add a negative dmt VE on each side. Yeah, put the dmdt on the other side of that. So we got m dvr dt. I did this already in the calc-based version. Multiply by dt on each side and divide by m, you get dvr, and that's similar to what I did last time. Multiply by dt on each side and then divide by m. That looks similar to what I did last time. I had delta V equals VE delta M over M. Just earlier, I just erased. Well, yeah, but that's kind of a different, that's for a small amount. To get the actual big picture, as they say. And there's a lot of ways this can get written, guys, but if you integrate from VRI, the initial speed of the rocket, to the final speed of the rocket of dVr, that's equal to negative MRI to MRF. Well, this is a bigger mass. The initial mass of the rocket is bigger than the final mass of the rocket because the rocket loses mass by expelling exhaust. And it's dm over m. Well, this integral is a famous integral. It's the natural logarithm. There's a VE right here. So let me see. I didn't put a VE here. I'm sorry, guys. VE right here, and there's a negative. So sort of running out of room a little bit. But so what we're talking about is looking like that. Well, if you do these two, this will become a true delta R. The delta R I wrote earlier was a really small delta R. It's valid, but only for very small increments in velocity. So it's a little deceptive that way. This right here, you do this integral, dVr, integrate dVr, you just get VR evaluated between VRF and VRI. It's just VRF minus VRI, which is delta VR. So delta VR, when you integrate this, you get that. When you integrate this, you get ln of m associated with these two. That's the natural logarithm of MRF minus the natural logarithm of MRI. Subtraction of logarithms is the logarithm of the quotient. So it's ln MRF. It's ln of the quantity MRF over MRI, and there's a negative right here. ln, and there's a lot of ways to go here, guys. The way, we don't want to think ourselves into a circle on this thing, but I'll try to just get us through it. For this right here, and you saw me, and I'll write this in a little different manner in a second, guys. You can interpret this a bunch of ways. If you're going to take, that's a positive quantity. Why the negative here? Well, what is ln? See, MRF is a small number compared to MRI. They're both positive. Positive divided by positive is a positive answer. A small positive number divided by a large positive number. Why is this large? Well, initially the rocket was full of fuel. After it exhausts a lot of the fuel that it burns, it's got less mass. This is less massive than that. Small divided by big, both positive numbers. Now, remember, small divided by big is a positive number less than 1. The ln of the natural logarithm of a positive number less than 1 is a negative answer. Negative times negative will give you a positive change. You can kind of look at it that way. You see, it's the reason there's no negative here is this is already going in the opposite direction. So you can kind of look at it that way. And this is a loss, so this is negative and negative, give you a positive answer. It's a bit confusing, guys. I'll be the first person to tell you that. The big thing is if you have the magnitudes under control, they're frequently going to ask you, what is the magnitude? What is the magnitude of the thrust? What is the magnitude of the rate at which exhaust is being expelled? What is the magnitude at which fuel is being expelled or being used up and expelled? What's the magnitude of that? What's the magnitude of the change? So a lot of times the negative is not going to be too much of an issue. The bottom line is the argument kind of, it's a pretty strong, the argument is how you do the calc based on it, and then the non-calc, get into that in a second. And there's, like I said, there's just a number of ways this stuff gets written. And a number of ways it can be visualized. the idea of the positive and negative, I don't want to say it's definitely not subjective, but it depends what you're defining to be what. As long as you have it straight, as long as you know that the exhaust speed is what it is, and the velocity of the exhaust is going in the opposite direction in which the rocket is moving, that's a big thing to know. So the look here, just try to see, and they give, like I said, they give different ways of looking at it here. Okay, so that's more of a calc treatment of it. And then as far as like the other, you're going to be looking at essentially the same thing here, guys. The non-calc. All right, for the non-calculus, you're talking about, they just say VF minus VI. That's the delta VR, same thing. They got some fancy notation on there. And that's equal to VE, which is going in the negative direction. Well, no, they say it's going in the positive direction. Yeah, this is where it gets a little on the messy side. You got to watch out. They're saying the initial, they put the initial on top. Why are they doing that? They want to get a positive answer for sure. And with the non-calc, maybe that creates less confusion for people. Initially, the rocket's got more mass than it finally has. Wait a minute, what were we doing? Here, yeah, I know, I said afterwards it's got less mass than it initially had. Right. Less, small divided by big is a number less than 1, still positive. A number less than 1, the natural logarithm of a number less than 1 is a negative answer. If you flip these upside down, it's not going to be a number less than 1, it's going to be a number bigger than 1. This is here we had small divided by big. We got a number less than 1 was positive. The ln of a number less than 1 but positive is a negative answer. The natural logarithm of a number less than 1 that's positive is going to be a negative answer. The natural logarithm is going to be a negative answer. The natural logarithm of the reciprocal of that number that was less than 1 is a number bigger than 1. Mi is bigger than mf, which means this is a number bigger than 1. The natural logarithm here is going to be a positive number. Positive times positive is going to give you a positive rate of change. Yeah, I know, but how are they the same? Well, the reason for that is, guys, if you took ln, there's a lot of ways to write this. Let me just try to make some sense. ln this minus ln this is equal to ln of MRF over MRI. Period. End of the story. If you reverse the order, MRI, ln MRI minus ln MRF is it's the same argument, but it's going to be ln of MRI over MRF. Well, how are they different? I don't know. If you got an answer here and the answer is X, let's make it straight. If this is A minus B and this is B minus A, the absolute value of the answer does not change at all. If this right here was A minus B, here's A, here's B, and now you put B over here and A over here, B minus A, how are they different? B minus A equals -1 times A minus B. They're not different in terms of magnitude, they're different in terms of sign. So you're not going to get the wrong answer in terms of magnitude, but you got to be able to get the right, just watch out. The signs are going to be different. So what does that mean? Well, it means this. It means if you took this right here, I'm just trying to follow their logic. If you put a negative in front of this thing, you'd have to put a negative in front of this thing. And a negative of this is the same as a positive this. Well, this is a problem. Not really. Small divided by big is a ratio less than 1, but a positive number, the ln of that is negative. This is positive times negative is another negative. Negative times negative is still a positive answer. Forgive the alphabet soup, guys. There's a lot of ways this can be written because the derivation itself is, you know, I don't want to, it's not confused. It's a great derivation. I mean, you saw the calculus that gets done to do it. Either way is going to work. Either way is going to work on this. And that's why they're pulling something like this, and they got the F on top and the I on the bottom, and here they got the I on, you know, they had, over there they got the F on top and the I on the bottom. Here they got the I on top and the F on the bottom. I can put the F on top too. It ain't going to differ. These aren't going to differ in terms of magnitude. They're not going to differ in terms of magnitude. It's just going to be a matter of sign when we do that. So ln, let's just speak that. So you guys in the non-calc, I mean, all of these mean the same thing, you guys, if when interpreted correctly, obviously. Okay, so we got that. We looked at it. We were making moves earlier, you guys, and we said what it was going to be. And like I said, for the thrust, it's this. Just put a delta put deltas instead of D's, and you're there. The instantaneous thrust capital MA. Yeah, it is. That's capital. Yeah, that's the throw. Now that we did, that one came out just right. We didn't have to wheel and deal with that one too much. And that one right there is, in fact, even to cover us, I appreciate that they do that actually here. They're saying whatever you want to call VE, and I'll put a capital there because I've been using capitals elsewhere, but the Serway and Buell do not. Again, it doesn't matter. That's delta M, delta T. That right there. So all of this is pertaining to the thrust, and all of this is pertaining to the change in velocity. That's for the non-calculus students. For the calculus students, you can write it like that. You know what? For either group, they're the same thing. They're just different language here. If you can get it down to here, you got it under. The calc students got it under control when they get to here too, just like the non-calculus students got it under control when they get to here as well. Here, again, if it's a functional difference, there are some things that could happen, but essentially, if it's a constant rate of change of expulsion, a constant rate of expulsion of matter in terms of exhaust, in the form of exhaust, constant rate of expulsion of exhaust per unit time, this works just as fine in the calculus realm too, if delta M over delta T is the same as dmr dt. You don't even have to put an R there. You know, part of the rocket is what it is, but whatever. This is like delta M over delta T. This is more precise if it's a variable amount at which it's leaving. If it's leaving at a constant rate, this is every bit as valid as what's valid over there. So that's just something I needed to tell you. I'm sorry, it's kind of like you're looking at both. Basically, both are the same, like I just told you. Be mindful of it. You've got the notes, and deal with it, okay? There was problem number, I'm trying to think here. Problem number 30 in chapter 9. They talked about, can we write something down? Can we get this thing right? Give me 1 second, guys. Let me just make sure it's on the mark. So let's see something else here, guys, if we could. For problem number 30, part C, they were saying, what if there was something here? And like I said, for the people in the 120, for the people in the non-calc version of this, it's a lot easier for you guys. All you got to do is, when you're doing a multiplication, I mean, I'll give you kind of something to kind of look at. All right, guys. Like I said, we talked about finding the work done, and we said it's force vector dot displacement vector, and we went into a vector dot b vector, being with a vector being ax I hat plus ay j hat plus az k hat. We thoroughly beat this up in the notes. We thoroughly beat this up in the notes on Canvas and in the films and in person when we lectured this stuff, you guys. So we know how to do this. You guys, we're here. We know how to do the dot product. When we get to here, when you do the dot product, it's the magnitude of you do the dot product, it's the magnitude of a vector times the magnitude of b vector times the cosine of theta between them. And that's also equal to, surprisingly, and derivable in all circumstances, ax bx plus ay by plus az bz. And so if there was something here to do this, this is calculus and non-calculus, guys. We talked about this. So let's see what we have here, guys. True, and if you were doing this, if the force vector was fxi plus fyj plus fzk, a lot of times they're not even going to go in 3 dimensions, guys. The problem I'm about to do from problem number 30 just goes in 2 dimensions. But if they want to go dxi, dyj, dzk, if you do the dot product, that's fx dx plus fy dy plus fz dz, which is also equal to simply the magnitude of f times the magnitude of d times the cosine of theta. That's an easier one to do if you can find it. But all this is valid. This applies for calculus and non-calculus. Well, that's not a real big deal. The d that I'm talking about here is not a differential. I want to make this clear. This d sub x is not dx. This is a differential. This is not. This is d sub x. I would almost want to use something, you almost want to use something else here just to kind of not have that. This is displacement of s, I don't know, s vector. Can't write s's too good, though. That's my thing. But they look like 5s when I write them, but here we go. So I'll try not to make them look like that. But does everybody understand here? This is, so just to kind of have it right. Look, it's not that. Yeah, something looking like that. So whatever, guys. You know where we're coming from, guys. Well, yeah, that's okay if the displacement is, and usually we're dealing with displacements that are easy to visualize. They might be along a line, let's say. But even here, you got to be a little careful. If it's kind of a straight line sort of thing, at least for a short period of time, at least, for the short period of time that you're discussing it, the displacement's in a straight line and the force is constant. If the force is constant over that period of time, this is a good way to go for everybody. But when it varies, you have to do an integral, and that's where the calc-based version of this mechanics comes in. You don't have to know this for the non-calc-based discussion, you guys. But, it's just something I want to tell you about. Let me quickly, so this is more of the calc-based one, and I think that'll be about it that I want to say beyond this. All right, guys. Well, if there's if there's varying quantities, if there's constantly varying quantities, as there is in problem number 30, they were showing a particle. I'll try to make it. I'll read it and then kind of just summarize it a little bit. This is from the Cat's book, and like I said, anybody wants to listen to it. The guys in the calc-based version of the mechanics. This is something you need to know. For problem 30, a particle moves in the xy plane from the origin to a point having coordinates x equals 7 meters and y equals 4 meters under the influence of a force given by F vector equals 3y squared I hat plus xj hat. I'm going to look at C. What is the work done on the particle by the force F if it moves along path 3 shown in green? I'll kind of make a long story short here, guys. For problem number 30 from the Cat's book, problem 30C from Dr. Katz's book. They're showing something like this. They're saying, okay, there's a path they want you to take. And they're saying you're going to go a total of 7 over and 4 up. So this is the path, it's doing that, and this is the path they want you to deal with. From 0, 0 to 7, 4. And that's in meters. And you have to follow this path, and you're dealing with a force, and you're dealing with the force vector is equal to, dealing with the force vector is 3y squared I hat plus xj hat. I hat plus x j hat. Did I read that right? I think I did. Right. So F vector equals 3y squared I hat plus F vector equals 3y squared I hat plus xj hat. And it's right here. So this is every time you find yourself in a particular location in the xy plane, this is the force in that location with x and y, with any point x comma y in the xy plane has this kind of force working on it. So in other words, where are you going to be? Well, wherever I am in the xy plane, whatever the x coordinate is and whatever the y coordinate is, I plug it into here, and that's the force vector, going in the I hat direction plus the vector sum of, this sum right here going in the I direction and going in the j direction. That's the force vector for a particular location anywhere in the xy plane with coordinates x and y. Well, I tell you what, let's get out of this. This is a straight line. as x proceeds this way, you get y values that way. Wait a minute. If you run 7 and climb 4, if you run 7, forgive me, yeah, if you run 7 and climb 4, you climb 4 for every run of 7, y equals 4/7 x. If that's the case, I'm going along that path. I'm going to go from x equals 0 to x equals 7, comma 0 right here. I know it's 7, comma 4 up here, but I'm going from here. I'm going from 7. I'm going from 0 to 7, and then I'm climbing up 4. I'm going to follow this path. What are we talking about here? Well, dr vector, there's a lot of ways you can go here with this one. It's dx I hat plus dy j hat. Yeah, great. So what? Well, what that means is dr vector is going to be dx if for every movement of x, the dx is indeed just dx. And for the y, well, if y is equal to 4/7 x, dy dx is 4/7. dy is 4/7 dx. So that's what dy is. The other one's a little different. The x, the x value equals x. So dx dx of that is dx of this, which is just 1. dx equals 1 multiplied by dx equals dx. Well, I'm not saying anything too profound here, guys. It's going at a normal speed, nothing crazy. In other words, you're parameterizing with respect to x. So x, the differential of x if x is the means by which we're going to parameterize, x is our measuring stick. So x moves at its own speed, and we call it dx. Y moves at dy dx, which is 4/7 x, d of 4/7 x dx, which is 4/7. So it's a little different dynamic right there, guys. So at the end of the day, you got this right here, and dx equals just 1. It's going at the speed 1. So dy is dx is 1x, and dy is 4/7 x. That's dx, and this is 4/7 dx rather, j. Well, okay. So if you're going to do this, a lot of ways you can write it. R is the way I wrote S. I wrote S earlier. I wrote D earlier. Just be consistent. This is all right. The R like this is fine. So what do you think? I mean, this is actually the way it's going to go. You're going to basically say that the work done is the integral from x equals 0 to x equals 7 of f vector dot dr vector, which is the work is going to be the integral from x equals 0 to x equals 7. F vector, they gave us F vector. It's a rough one, but we can do it. Be faithful to what's up there and remember what the definition of the dot product is. You got that there, that quantity, absolutely that quantity. Dot dr vector. Dr vector is dx I hat plus dy j hat. Here goes. Integral from x equals 0 to x equals 7. Yeah, watch out. Now, what did we say? Remember what we were saying earlier. We said that y, we said that y was equal to 4/7 x. What does that mean? Wherever you see a y, put 4/7 x in it. 3. The y is 4/7 x. That's the language they're talking. Plus, stay the x, because you did this in terms of x. Forgive me. Yeah, it is dy j hat, but what is dy? Man, we just delivered that speech earlier. dy is 4/7 dx. What have we accomplished here? What we accomplished here is everybody's dx and everybody's x. X equals 7. Here we go. Go ahead and dot it, and let's see what happens here. I hat and I, you go the x's together. Well, you know who the x's are. Everybody's x's, but go the I hats together, and you get, go the I hats together, and you end up getting, what is this? 16 over 49 times 3. That's 48 over 4, right? That's 16, square this, that's 16 over 49 times 3, that's 48 over 49 x squared. 48 over 49 x squared. There's a dx here. Sounds good, we'll take care of it. And go over here. 4/7 times x dx. Oh, yeah, that's okay. That's okay. You just factor the dx out of there, you guys. And let me just do that. There's a lot of stuff here you don't want to erase, but you got to erase some of it. What do we got? Well, I'm gonna pull. There's a dx here and a dx here. I can make them two separate integrals or unite them as one integral. The big thing is we got it in terms of one variable. We parameterized it in terms of the variables present. You could have parameterized it in terms of t. You could have parameterized, as we've done in other cases, as I've shown in the notes in other cases, other things to talk about. But you didn't have to. You could parameterize with respect to some t, or for the speed of which things are happening, or parameterize it with one of the variables because the two variables are related to each other. You figured out that this was a line, straight line of slope 4 over 7. 4 over 7. So y equals 4 over 7 times x. So you got that, and it's doing this. It's 48 over 49 x squared plus 4/7 x, the whole thing dx. Those in the 120, they're not going to take you down this road for sure. The other thing with the bullet hitting that sort of pendulum, that block that was attached to the metallic rod, and the metallic rod went all the way to the top, yeah, it's conservation of momentum, that's conservation of energy, no calculus there. Something like that could happen in some place or another. But not this right here. The calculus base of this is more for is obviously for the calc-based class. Well, okay, let's do it. Let's integrate this thing. Use the power rule. It's going to be kind of like all over the place on this, but it's going to end up as 16 over 49 x to the third. This right here is going to be 2/7 x squared. We're going to evaluate between 0 and 7. Well, 0 is the easiest number to deal with in the world regarding something like this, because you got an x squared here and an x to the third there. Those are the variable quantities that are within both of those functions. They're the only variable quantities within both of these functions right here. They're the only variable quantities there, and it's x squared, x to the third, put a 0 here, that's nothing. Go over here, then put a 7. Put a 7 right here. Well, there's 3 of these 7s multiplied together. There's 2 7s down here multiplied together. They cancel. You just got a 7 right here. This becomes 112 right here. And then go right here, a 7 right here. There's 7 times 7. There's a 7 on the bottom here doing a division. So it's just 7 times 2 is 14. Okay, so it should be that. Now let's see. Unless I made a careless mistake, guys, I think we're okay. I think we're okay. Or are we okay? Yeah, I think we're okay. It looks like it. Let's just make sure I finished the math okay. Yeah, 126 joules, guys. Why? Yeah, great. I told you unless I made a careless error, and there it was. That's 126 joules. If you do this down a different path, you're getting different answers, which tells you that the force field is not conservative. It's not conservative. But this is what we got here. Now, they could have said to you, they could have really tried to pull a fast one on you. They could have said that this thing was, I don't know what to tell you. They could have given you the length of this thing and said that there was an angle. It's coming from an angle, this is 90 degrees. Guys, ladies and gentlemen, this is 90 degrees right here, and this is some angle theta. And somebody says to you, well, we're rotating, we're going to rotate from the negative y-axis, we're going to rotate from the negative y-axis counterclockwise and amount 90 degrees plus theta. And there's your theta to bring you to here. And they might tell you how long that thing is. Then you got to figure it out. Wait a minute, that's a straight line. If I get the cosine of theta, I'll know how long it is down here. If I go cosine, they might tell you how long this is. I don't know how long it is. They could say this is 7, this is 4. This is a rough one. I mean, if this leg is 7 and this leg is 4, then c squared equals a squared plus b squared. C is equal to the square root of, 7 squared plus 4 squared. C equals, that's 49, that's 16, right? 7 squared is 49, 4 squared is 16. 49 and 16 is 65. 49 and 60, that's almost 64. Let's say they constructed it and it was 64. What's the square root of 64? It's 8. If this is 8 meters long, if this is 8 meters long, 8 times the cosine of theta will give you this. 8 times the sine of theta will give you that. You can find y over x for anything on the straight line. That'll be the slope. The slope here happened to be 4/7. Or you leave it at 65, which is 8 point something. 8 point something. 8 point something times the cosine of theta will give me this, which is 7. This is 8 point something. This is the square root of 65. This is the square root of 65. The square root of 65 times the cosine of whatever the theta is. I don't care about the 90. They told me this thing went 100-something degrees. 90 of it got eaten up right here. It rotated from the negative y-axis counterclockwise and rotated up this way to whatever degree measure. We'll get the degree measure, get the cosine of the degree measure, square root of 65, get an answer, 8 point something, times the cosine of theta will give you 7. Square root of 65, 8 point something, times the sine of the theta will give you 4. This is 4, this is 7, and then you could still derive it like this. They didn't do that here. Here they already gave it to us. They already gave us, hey, it went 7 over and it went 4 up. But what if they just say, hey, man, that thing's a little more than 8 long, a little more than 8 meters long. It started here. It rotated up, and let me resolve it. Let me find what that is. Let me find what that is. Okay, that's for the calc-based people that are taking this. Okay? All right, guys, take a look at it. Look at your notes. I'll try to be as fair as I can be for the stuff that's coming up. And best of luck to you. Thank you for your time.